Hello, it's Mr. Cerisa, and this is a special request from Estelle. She would like to learn more about solving airplane problems with horizontal and vertical components. So here's the example I came up with as the drone flies with a bearing of south 30 degrees west with a speed of 32 miles per hour. It gets caught in a wind with a speed of 28 miles per hour heading due west. What is the ground speed of the bearing and the bearing of the drone? Okay, so let's first put in these different vectors, and the first one would be the drone, and that is going south 30 degrees west. So I started at south and I moved west 30 degrees. And this one has a speed of 32 miles per hour. And then we have the wind, which is blowing at a speed of 28 miles per hour due north. So that means it's going straight up north. And this is 28 miles per hour. And so we know there's two ways of solving these, or two main ways. And one is using vectors, and the other is with the triangles. And I've already made one using triangles, so this will be just for using the vectors. So first we need to figure out the two vectors. One will be the wind, and this vector, since it's going due north, that means it only has the j component, because that's the up-down, and it will be positive 28 because it's going up. And then the other one is going to be the drone. And the drone, we know, is going 30 degrees west from south, or south to west, and so we have to figure out what that angle really is. So we're looking for the angle all the way around, and that angle, as you can see by the picture, is 180 degrees plus, and then the 60 degrees that completes it until the south 30 west. And then we also need the radius, or if you want to think of it as the magnitude of the resultant vector, that's the 32. So let's create these components. The horizontal component is just going to be the magnitude times cosine of the angle. So I didn't finish this off, and this was 240. So cosine of 240 degrees. And that's your I, that's the horizontal component. And that will be added to the vertical component, which again is 32. And then this time it's going to be sine 240 degrees. And that's our J. And so we have the horizontal and vertical component. And if we add the drone to the wind, let me rewrite the wind down here so it's a little easier to see it together. But the wind is just the J, and so that's the 28J. And if we add them together, we'll get the resultant vector. And a lot of times this is considered like the ground speed, etc. And so the resultant will be the I is just the 32 cosine of 240. So let's work out that cosine of 240 first. And you can see from the picture that that's really a 30, 60, 90 triangle right there. And so that part will be 60 degrees. So this 240 acts just like a 60 degree, except for it's in the third quadrant, which makes it negative. And then 60 degrees would have a cosine of 1/2. So 32 times negative 1/2 is negative 16. And again, that's our I. And then same thing's going on here. The sine of 240 will be the same as sine of 60, but it's in the third quadrant. So that will be negative radical 3 over 2, which means minus 16 radical 3. And then finally we're adding that to 28. And so actually let me set it up this way with a plus negative 16, and that's our J. Okay, so that's our resultant vector. But that's not what the question's asking. The question's asking what the ground speed and the bearing will be. And so, starting with the ground speed, that will just be the square root of the x squared plus the y squared. So the x is -16, so that will be squared, plus the y, which is complicated, so make sure in your calculator you keep it in parentheses. So -16 radical 3 plus 28, and that whole thing is squared. And when you square that out, it comes to almost exactly 16. So 16.0, and that's in miles per hour. And so that's the r, and then finally the theta. Remember, the tangent of theta is going to be our y over our x. That's true every time. People forget, but the tangent of theta is y over x. And so our y is -16 radical 3 plus 28. And our x is the -16. And then, so when we work that out, we take the inverse tangent. Let's do that here. The inverse tangent, and we end up getting our theta equaling -1.028. But that doesn't really make any sense for -1.28, because that puts the angle into the fourth quadrant. And you can see, if I move, let me get rid of this red line, but if I move our wind vector to the end of this vector, it's going to go up. So there's no way that will end up being in the fourth quadrant. So that doesn't make any sense. So that should tell us, okay, if it's going southwest and the wind is blowing it north, it's going to end up either in the third or the second quadrant. And if I add 180 degrees to it, it'll move it from the fourth quadrant to the second quadrant. And that will end up being 179 almost exactly degrees. Okay, so the only problem here is this is in degrees, and we want it as north something west. So if we look at how that's all set up, we can see that it ends up being north 89 degrees west, and that will be our final answer for our bearing, and the 16 miles per hour is the final answer for our ground speed. Okay, thank you. I hope this helped. Thank you, Estelle, for listening.